1700 Cascadia earthquake. A magnitude 9 megathrust earthquake ruptured 1,000 kilometers of seafloor, sending tsunamis across the Pacific. On a winter evening in January 1700, the Pacific Northwest coast of North America experienced one of the most powerful earthquakes in recorded history, yet for nearly 3 centuries, Western science had no knowledge of its existence. The event remained hidden in geological layers, preserved in Japanese historical documents as a mysterious orphan tsunami, and carefully maintained in the oral traditions of indigenous peoples who experienced its devastating power. This was the 1700 Cascadia earthquake, a magnitude 8.7 to 9.2 megathrust event that ruptured approximately 1,000 kilometers of the Cascadia Subduction Zone from mid-Vancouver Island to northern California. The earthquake matters profoundly because it revealed that the Pacific Northwest, now home to over 10 million people, including the cities of Seattle, Portland, Vancouver, and Victoria, faces catastrophic seismic and tsunami hazards comparable to those that devastated Japan in 2011 and the Indian Ocean in 2004. Before the 1980s, scientists believed the Cascadia Subduction Zone was incapable of producing great earthquakes, despite recognizing the tectonic boundary since the mid-1960s. The zone appeared seismically quiet with no major earthquakes in written history, lulling the region into a false sense of security. The discovery of the 1700 event revolutionized understanding of North American earthquake risks and validated indigenous knowledge systems that Western science had long dismissed. It demonstrated that megathrust earthquakes can generate trans-Pacific tsunamis and established the scientific framework for assessing future hazards in a densely populated region. Today, scientists estimate a 37% probability of a magnitude 8.2 or greater earthquake within 50 years, and a 10 to 15% probability of a magnitude 9 or greater event rupturing the entire zone. The 1700 Cascadia earthquake serves as both a scientific milestone and an urgent warning that the clock is ticking toward the next great rupture. The 1700 Cascadia earthquake resulted from hundreds of years of accumulated geological tension at one of Earth's most significant tectonic boundaries. The Cascadia Subduction Zone marks where the Juan de Fuca plate, a relatively small oceanic plate, slides beneath the much larger North American plate at approximately 4 centimeters per year. This movement might seem gradual, but it represents an inexorable collision of titanic forces that builds catastrophic potential over centuries. At depths shallower than 30 kilometers, the two plates become locked together by immense frictional forces, preventing the smooth sliding that would release energy gradually. Instead, the North American plate is dragged downward and compressed as the Juan de Fuca plate continues its relentless descent into Earth's mantle. Stress accumulates year after year, decade after decade, century after century, deforming the rock and storing elastic energy like a colossal spring being compressed beyond its limits. Geological evidence reveals that great earthquakes with magnitude 8 or higher occur in the Cascadia Subduction Zone approximately every 500 to 600 years on average, though the interval between events ranges from 300 to 900 years. Scientists have documented at least 13 such events in the last 6,000 years, establishing a pattern of recurring catastrophic ruptures. By January 1700, the fault had accumulated sufficient strain to exceed the frictional strength holding the plates together. When the locked zone finally failed, it did so catastrophically and nearly instantaneously along approximately 1,000 kilometers of the fault. The North American plate rebounded upward and westward, releasing centuries of stored energy in minutes of violent shaking. The average slip along the fault reached 20 meters, an enormous displacement that thrust the ocean floor upward and set in motion a devastating tsunami. Chapter 3: A Seismically Silent Zone. Throughout the 19th and 20th centuries, the Pacific Northwest coast developed under a dangerous misconception about its geological character. Unlike the earthquake-prone regions of California, Alaska, or Japan, the Cascadia coast appeared remarkably quiet, with no major earthquakes recorded in written European-American history. When geologists recognized the Cascadia Subduction Zone as a plate boundary in the mid-1960s, they faced a puzzling contradiction between the tectonic setting and the apparent absence of great earthquakes. Subduction zones around the world, from Chile to Alaska to Japan, regularly produce the planet's most powerful earthquakes. Yet Cascadia seemed different, leading many scientists to theorize that the zone might release its energy through slow, aseismic creep rather than catastrophic ruptures. This assumption shaped building codes, land use planning, and public awareness throughout the region for decades. The indigenous peoples of the Pacific Northwest, however, maintained detailed oral traditions describing catastrophic earthquakes and tsunamis. The Huayat, Cowichan, Quilote, Makah, Nuai Cha Nulth, and other tribes preserved stories of nighttime earthquakes so violent people could not stand, of shaking so prolonged it made them sick, and of devastating waves that destroyed entire villages. These accounts included specific details about coastal subsidence, the destruction of settlements below certain elevations, and the complete annihilation of communities with no survivors in low-lying areas. Western science largely dismissed these traditions as mythology or exaggeration, particularly stories involving supernatural beings like Thunderbird and Whale engaged in cosmic battles. The seismic silence continued to reassure settlers and developers that the region was fundamentally safe from catastrophic earthquakes. This dangerous complacency persisted until the 1980s, when pioneering scientists began uncovering geological evidence that would transform understanding of the Pacific Northwest's true seismic character and validate the knowledge indigenous peoples had carefully preserved for nearly 3 centuries. The scientific discovery of the 1700 Cascadia earthquake represents one of geology's greatest detective stories, piecing together evidence from multiple disciplines and continents. In the 1980s, U.S. Geological Survey geologist Brian Atwater began investigating coastal marshlands in Washington state and discovered buried layers of peat and soil suddenly drowned by salt water and covered with younger sediments. These ghost forests of red cedar trees, standing dead in tidal zones where they could not normally survive, told a story of rapid coastal subsidence. Atwater's work revealed that coastal regions had dropped 1 to 2 meters instantaneously, with some locations subsiding up to 12 meters, drowning marshlands and forests that were subsequently preserved in the geological record. The evidence showed at least 13 such events in the last 6,000 years, establishing a pattern of recurring great earthquakes. Caltech geophysicists Tom Heaton and Hiro Kanamori contributed crucial research demonstrating that the Cascadia Subduction Zone was indeed capable of producing magnitude 9 earthquakes. The breakthrough came in 1996 when Japanese seismologist Kenji Satake and colleagues made a remarkable connection. Japanese historical documents recorded a damaging tsunami that struck nearly 1,000 kilometers of Japan's Pacific coast on January 27, 1700, with wave heights of 1 to 5 meters. This orphan tsunami, arriving without any earthquake felt in Japan, had puzzled historians for centuries. By modeling tsunami propagation across the Pacific Ocean, Satake determined that only a magnitude 9 earthquake along the entire Cascadia Subduction Zone could have generated the observed tsunami in Japan. The timing calculations were remarkably precise, indicating the earthquake occurred at approximately 21 Pacific time on January 26, 1700, with the tsunami reaching Japan approximately 9 hours later. Dendrochronologist David Yamaguchi provided the final confirmation through tree ring analysis, demonstrating that the ghost forest trees died after the 1699 growing season, dating the event to winter 1699 to 1700. Chapter 5. 4 Minutes That Changed Everything. At approximately 21 Pacific time on January 26, 1700, the Cascadia thrust fault ruptured catastrophically along its entire 1,000-kilometer length. The shaking began suddenly and intensified to levels that made standing impossible, continuing for an estimated 4 to 5 minutes or longer as the rupture propagated from south to north or north to south along the coast. Indigenous oral traditions describe the violence with vivid detail. Houses of the Cowichan people on Vancouver Island collapsed, landslides cascaded down slopes, and people were thrown to the ground by shaking so prolonged and severe it induced nausea. The earthquake released energy equivalent to centuries of accumulated tectonic strain, with the North American plate rebounding upward and westward by an average of 20 meters along the fault. As the shaking subsided, coastal residents faced an even more terrifying threat. The massive displacement of the ocean floor generated a tsunami that struck the Pacific Northwest coast within 15 to 20 minutes, with wave heights potentially reaching 24 to 30 meters in some locations. The winter village of the Pachena Bay people on Vancouver Island was completely destroyed, with no survivors in settlements below 23 meters elevation. Multiple indigenous villages were wiped out entirely, their locations preserved in archaeological records showing flooding and abandonment around 1700. The tsunami swept across the Pacific Ocean at the speed of a jet aircraft, reaching Japan before midnight on January 27, Japanese time. Along nearly 1,000 kilometers of Japan's eastern coast, waves of 1 to 5 meters struck without warning. At Kuagasaki, 13 houses were destroyed by flooding and 20 more burned in a subsequent fire. Salt kilns were damaged, fields and paddies flooded, and at least one fatal shipwreck occurred. The earthquake had generated a trans-Pacific catastrophe, linking the fates of communities separated by an ocean in a single night of destruction that would echo through centuries. Within 15 to 20 minutes of the initial rupture, massive tsunami waves struck the Pacific Northwest coastline with catastrophic force. Coastal regions that had suddenly subsided 1 to 2 meters, with some areas dropping as much as 12 meters, were immediately inundated by walls of water reaching heights of 24 to 30 meters in some locations. The winter village of the Pachena Bay people on Vancouver Island was completely obliterated, with no survivors recorded in settlements below 23 meters elevation. Multiple indigenous villages along the coast suffered similar fates, their locations chosen over generations suddenly rendered deadly by the combination of subsidence and tsunami. The tsunami swept inland, carrying away houses, canoes, and everything in its path. Survivors who had fled to higher grounds during the earthquake watched helplessly as their communities vanished beneath the waves. Red cedar forests along the coast, suddenly plunged into the tidal zone by subsidence, began their slow death as saltwater infiltrated their roots, creating the ghost forests that would puzzle scientists centuries later. 9 hours after devastating the North American coast, the tsunami reached Japan shortly before midnight on January 27, 1700, Japanese time. Wave heights of 1 to 5 meters struck along nearly 1,000 kilometers of Japan's Pacific coast, from Tanabe to Miho. At Kuagasaki, 13 houses were destroyed by flooding and 20 more burned in fires that followed. Salt kilns were damaged, fields and paddies flooded, and at least one ship was wrecked with fatal consequences. Japanese officials meticulously recorded the mysterious tsunami in historical documents, noting with confusion that no earthquake had been felt to explain the waves. This orphan tsunami, as it would later be called, provided the crucial evidence that would eventually unlock the mystery of the 1700 Cascadia earthquake nearly 3 centuries later. Chapter 7. Unlocking the Geological Mystery. The scientific investigation that revealed the 1700 Cascadia earthquake unfolded across decades and continents, combining multiple disciplines in an unprecedented collaborative effort. In the 1980s, United States Geological Survey geologist Brian Atwater began excavating coastal marshes in Washington state, discovering buried soils and ghost forests that indicated sudden subsidence events. His work revealed layers of sand deposited by tsunamis overlying subsided marshlands, with the most recent event showing distinctive characteristics. Simultaneously, Caltech geophysicists Tom Heaton and Hiru Kanamori challenged the prevailing assumption that the Cascadia Subduction Zone could not generate great earthquakes. They argued that the zone's seismic silence indicated locked plates accumulating strain, not geological safety. The breakthrough came in 1996 when Japanese seismologist Kenji Satake and his colleagues connected historical Japanese tsunami records to the geological evidence from Cascadia. By working backward from the documented arrival times of the orphan tsunami at 7 locations along Japan's coast, they calculated that the source earthquake occurred at approximately 21 Pacific time on January 26, 1700. Dendrochronologist David Yamaguchi provided crucial confirmation through tree ring analysis of ghost forest cedars. The trees showed their final growth rings formed in the summer of 1699, with death occurring during the subsequent dormant season, perfectly matching the January 1700 date. University of Washington researcher Ruth Ludwin contributed another vital piece by systematically documenting Native American oral traditions. Stories from the Huai-Art, Cowichan, Quileute, Makah, and other tribes described nighttime earthquakes, prolonged shaking, and devastating tsunamis that matched the scientific evidence with remarkable precision. This interdisciplinary investigation revolutionized understanding of Pacific Northwest seismic hazards and established new methodologies for studying prehistoric earthquakes worldwide. The discovery of the 1700 Cascadia earthquake profoundly transformed the relationship between Western science and indigenous oral traditions, validating centuries of Native American and First Nations historical knowledge that had been systematically dismissed. Tribal accounts that described the earth shaking so violently people could not stand, shaking that lasted so long it made them sick, and massive waves that destroyed coastal villages were confirmed as accurate historical records rather than mythology. The Cowichan people's stories of houses collapsing on Vancouver Island, the Huai-Art accounts of Pachina Bay village destruction, and Quileute traditions of a nighttime flood matched the scientific evidence precisely. Cultural elements including thunderbird and whale stories, which described cosmic battles causing the earth to tremble and ocean to rise, gained recognition as metaphorical encoding of seismic events. Ritual masks, dances, and ceremonies commemorating the earthquake were understood as sophisticated methods of preserving and transmitting critical survival information across generations. This validation sparked broader recognition of indigenous knowledge systems as reliable sources of long-term environmental and geological history. The discovery also catalyzed practical responses within indigenous communities themselves. The Huai-Art, First Nation on Vancouver Island, initiated projects to relocate their community to higher ground, explicitly citing ancestral knowledge of tsunami risk. The Quileute Nation in Washington state successfully lobbied to move their reservation away from the tsunami zone, finally achieving land transfer in 2012. Public awareness expanded dramatically following the 2015 New Yorker article titled "The Really Big One" by Catherine Schulz, which brought Cascadia earthquake risks to mainstream attention. The article's vivid description of potential devastation sparked widespread media coverage, public discussions, and increased pressure for improved preparedness measures throughout the Pacific Northwest region. Chapter 9. A Region Transformed. The discovery of the 1700 Cascadia earthquake fundamentally transformed the Pacific Northwest from a region perceived as geologically stable to one recognized as facing catastrophic seismic and tsunami hazards comparable to the world's most dangerous zones. Scientists now estimate a 37% probability of a magnitude 8.2 or greater earthquake occurring within 50 years, and a 10 to 15% probability of a magnitude 9 or greater event rupturing the entire Cascadia Subduction Zone. With over 10 million people now living in the region, including major cities like Seattle, Portland, Vancouver, and Victoria, the stakes are extraordinarily high. Emergency management agencies throughout the Pacific Northwest developed comprehensive tsunami evacuation plans and mapping programs, identifying vulnerable coastal areas and establishing evacuation routes to higher ground. Blue and white tsunami evacuation signs now mark routes throughout coastal communities, and annual drills practice rapid evacuation procedures. Building codes were revised to incorporate seismic design requirements, though thousands of older unreinforced masonry buildings remain dangerously vulnerable. Critical infrastructure, including bridges, hospitals, schools, and emergency facilities, face significant risks, with many structures built before modern seismic standards were implemented. The region's major bridges, including those crossing the Columbia River and connecting Seattle, were constructed without full understanding of Cascadia hazards and may fail during a major earthquake. Tsunami warning systems were enhanced, though the Pacific Northwest's proximity to the fault means coastal communities may have only 15 to 20 minutes of warning before wave arrival. Despite these improvements, experts consistently warn that the region remains inadequately prepared for a full Cascadia rupture. The 1700 earthquake demonstrated that 3 centuries of accumulated strain can release catastrophically, and the current interval of 325 years approaches the historical average recurrence time of 590 years. Today, the 1700 Cascadia earthquake serves as both historical milestone and urgent warning, its legacy visible in ghost forests, geological records, and the transformed understanding of Pacific Northwest seismic risk. Along the coasts of Oregon and Washington, the skeletal remains of red cedar trees stand as haunting monuments to the event, their salt-bleached trunks rising from beaches and estuaries where they died 3 centuries ago. These ghost forests attract scientists, photographers, and visitors who see in them tangible evidence of geological forces that remain active beneath their feet. The earthquake's discovery established the scientific framework for understanding megathrust earthquake hazards and demonstrated the power of interdisciplinary research combining geology, historical records, dendrochronology, and indigenous knowledge. It provided crucial comparative data for understanding other subduction zones worldwide, particularly following the devastating 2004 Indian Ocean tsunami and 2011 Tohoku earthquake and tsunami in Japan, both magnitude 9.1 events with striking similarities to the predicted Cascadia scenario. Educational programs throughout the Pacific Northwest now teach schoolchildren about earthquake preparedness and tsunami evacuation, attempting to create a culture of readiness that did not exist before the 1700 earthquake's discovery. Museums and interpretive centers present the geological evidence and indigenous histories, ensuring public awareness of the hazard. Yet the region's continued growth, aging infrastructure, and incomplete preparedness measures create ongoing vulnerability. The Cascadia Subduction Zone continues accumulating strain at approximately 4 centimeters per year, the Juan de Fuca plate inexorably diving beneath North America. Scientists cannot predict when the next great earthquake will occur, only that it will happen. The legacy of 1700 is therefore not just historical understanding, but an ongoing imperative for preparedness, infrastructure improvement, and respect for the powerful geological forces that shape the Pacific Northwest coast.